I thought we could start by doing a warm-up problem. This was one I was thinking about doing last time, but we ran out of time. So now we have lots of time. With 50 minutes, surely we can get this done. Well, before we start, let's just say what the problem is. Find the critical points for, and here's this function f of xy, x squared y plus x squared minus 6xy plus y squared minus 6x plus 7y. So we're looking for the critical points. Did anybody find them? Now, maybe there aren't any. Maybe there's 1 or 2, 3, 4, 5. You know, just looking at the function, it's not obvious whether there are any and how many there will be. Did anybody find critical points? I see a hand up?
3, 1.
3, 1. Okay. So here's our candidates. I'll make a list. 3, 1. Is that the only point, or is that just one of them?
That's the only one I got.
All right. Any other critical points people found?
0, 7 halves.
0, 7 halves. Okay. All right. Could be. I don't know about the 3, 1. Any others?
1, negative 1.
1, negative 1. Okay. All right. Any more? I don't remember what there is, so.
5, negative
5, negative 1. All right. Last chance for bids? Okay, well, let's find out. Let's find out. Now, there's some keywords here. And, well, the key phrase is find critical points. If we see find critical points, what are we going to do? Yeah, we're going to find the critical points. Yeah, but what are we going to do to define them?
Find the gradient.
Yeah, we're going to set the gradient equal to 0. So if you see a find critical points type problem, you say, that's really saying set the gradient equal to 0. And when we talk about the gradient, that's really the vector, right? So it's f sub x, f sub y. And here when we talk about 0, it's the 0 vector. So more precisely, we could say, all right, we're going to set 0 is our partial derivative with respect to x, and 0 is our partial derivative with respect to y. Well, let's take our partial derivatives. We'll start with respect to x. What's the derivative with respect to x? 2xy plus 2x minus 6y minus 6. All right. How about f sub y, derivative with respect to y? X squared minus 6x plus 2y plus 7. All right. Good. 2 equations and 2 unknowns. Good times are ahead. Now we have to make a choice. How to proceed. And this is a little bit more challenging than our traditional 2 equations, 2 unknowns, because these aren't linear. They'll almost never be linear. Now, before we get too far, this problem is not meant to make you nervous. This problem is just meant for us to practice our algebra skills. On the exam, we would give you something more straightforward. So if you start feeling like this sense of dread building up, let it go. It's okay. It's okay. It's a process we want to make sure you understand. So how do we solve? So as a reminder, there's 2 basic tools we have. One we did last time is substitution. Do you remember what the other one is? We mentioned it. Not quite elimination. Factoring. Yes. Well, can any of these factor? Now, you might say, I don't know, how can I tell? And one thing you can look for is, you know, you're very used to factoring ax squared plus bx plus c. But there's various tools in your back pocket. One tool you can do is called just sort of grouping. So you look at this like expression and think of it in two parts. 2xy plus 2x minus 6y minus 6. What could you do with that? From the first part, 2x, y plus 1. From the second part, pull up the minus 6, y plus 1. Now, what do you see that they both have in common? Y plus 1. So the first equation factors as 2x minus 6 times y plus 1. Well, that's equal to 0. So it tells us there's one of two possibilities. Either the 2x minus 6 equals 0, or the y plus 1 equals 0. Now, if 2x minus 6 equals 0, what's another way to say that? X equals 3. Or y plus 1 equals 0. Another way to say that? Y equals negative 1. Now, that's just from the first equation. So x has to be 3, or y has to be negative 1. Unfortunately, that does rule out one of our candidates. I am sorry. It was a great guess, but that doesn't have x equals 3 or y equals negative 1. On a side note, all the others do, so that's promising. Okay. Well, let's pick a direction. We have to go down both of these paths. Which one do you want to explore first? X equals 3 or y equals negative 1?
X equals 3.
X equals 3. All right. Now, notice so far we've only used the first equation. Partial f partial x equals 0. We haven't done anything with f sub y. So we say, well, let's remind ourselves what's going on. We have the x squared minus 6x plus 2y plus 7 equals 0. Well, we're looking at x equals 3. So that becomes 9 minus 18, which is 6 times 3, plus 2y plus 7 equals 0. And this looks like we can probably solve it. 9 plus 7 is 16. Subtract 18 would be negative 2. We can move that across. This becomes 2y equals 2, or y equals 1. Now remember, x equals 3. And this says y equals 1. So 3, 1, definitely a point. All right, good. Phew. Now, we still have another branch. Y equals minus 1. Okay, well, let's see what that says. Well, that says x squared minus 6x plus 2 times negative 1 plus 7 equals 0, or x squared minus 6x plus 5 equals 0. What can we do for this problem?
Factor.
We can factor. Does x squared minus 6x plus 5 factor in a nice way? He says, as he writes it down. How does it factor? X minus 1, x minus 5. Which leads us to x equals 1 or x equals 5. But remember, we already said y is negative 1. So that gives us the point 1, negative 1. So that is a critical point. And 5, negative 1. So all three of those that are left are indeed critical points, and they are the only critical points. Phew. All right. A good algebra workout. Any questions? Now, I will say that most problems on an exam that start with the word find the critical points Usually don't stop at the word find. What's the other thing that you'll often see? Classify. And so that's where you pull out the material from last time using the second partials test. We'll talk a little bit about that today as a reminder. All right. Well, on to today. And start with our thought for the day from Grand Admiral Thrawn. This is a character from the Star Wars universe who said, "Do you know the difference between an error and a mistake? Anyone can make an error. But that error doesn't become a mistake until you refuse to correct it." Lots of us make errors. I make errors a lot. I've been feeling that way for the last week and a half, where I've made a lot of silly errors. It's okay to make errors. Making errors is not a sign that you are a bad mathematician or you're going to be a bad engineer or whatever discipline you choose to pursue. But you don't want to have them fester and become mistakes. Learn from your errors. That's how you get better. Grow. And so don't be weighed down by the guilt of making mistakes and, well, making errors. Rise up and get better. All right. Well, now what's our topic for today? I should note, we should have titled this Optimization Number 2, because last time we called it Optimization Number 1. So there's 3 days of optimization. And today's goal is very focused on a very particular idea. We want to find absolute max and min for a continuous function on a closed and bounded domain. So how will you recognize these problems going forward? If you see the phrases absolute max and min, that's a pretty strong clue. We'll talk a little bit next time as well about problems where they might use that phrase, but it gets a little dicey. Oh, there are stories to tell. Now, how do we do it? Well, you might notice there's somewhat of a colorful character here. Not quite seasonally appropriate, but let's pretend like it is. And I guess to get in the spirit, I did bring the hat. So, all right. So, just channel your inner, Christmas spirit. And there's a song that goes, "We're making a list and checking it twice. Gonna find out which points are nice. Absolute max and min are found." Right? That's the goal. So the whole spirit of today is we're making a list. And then we're going to check it. And then we're going to find out which points are nice. That's where we're going. Okay, so that's where we're going. Now, let's recall last time. So last time, we did the second partials test. And the second partials test, suppose you're at a critical point of a very special type. The gradient equals 0. Then we have this particular number that we compute, which comes from the second derivatives, the fxx times fyy minus fxy squared. And we evaluate that at the critical point that we're interested in. And then we look at the sign. We will see the sign, and it'll open up our eyes. If it's negative, that says a saddle. If it's positive, look in the slice, which means just look at the fxx, or you can look at fyy, doesn't matter, and see what that sign is. If that's still positive, local min. If it's now negative, local max. If it's 0, it's inconclusive. So the classify is you just carry through the test. The test is on the formula sheet, so you don't have to stress too much about remembering. But I added some words here that I didn't put in last time. And that's these words: local min, local max. So in other words, when you're applying the second partials test, it can only say that this critical point is a local min or a local max. It cannot tell you absolute min or absolute max. And why not? Well, essentially it comes from saying the second partials test came from looking at this Taylor polynomial. And at the critical point, the linear terms drop away. So the behavior is driven by this matrix, and that's where these pieces come from. But there's this squiggly line. That stands for approximation. It's kind of how the function behaves. And that approximation is good if you are near AB. And it gets bad if you're far away. But local min says what's happening nearby. So that's why I can still say local min versus local max. Absolute min, or absolute max, says I need it over everywhere. And so I cannot make any global conclusions because this approximation is only local. So, say, all right, that's fine. So what if we do want to find the global max or global min? Well, there's a big challenge. It might not exist. And you don't have to come up with very exotic functions. Here's a very simple function. F of x comma y is x plus y. It's a very harmless function. Now the only thing we're going to do is restrict the domain and says look in between x from 0 to 1 and y from 0 to 1. So there's a square. But you're not including the edges. Now, my question. What's the largest value for this function inside this square? Now, you want to say it's 2, right? But where would 2 be? 2 would be over in this corner. But the problem is that corner is not a part of our domain. But what can we do? Well, we can get close to 2 by getting closer and closer to the corner. So we can get arbitrarily close to the value of 2, but we cannot attain it in our domain. So we have issues. So we have to be careful. Global max and global min are not guaranteed to exist. But if we add some assumptions, then they are. So here's our assumptions. If you have a nice function, nice here, the definition, continuous. Doesn't even have to be differentiable, it just has to be continuous. And your domain is closed and bounded. Now we've used these words before. Do you remember what closed means?
Like solid lines instead of dotted lines?
Solid lines instead of dotted lines is a great way to think about it. You include your boundary. So this one, we are not including our boundary. It's the dotted lines. All right. So closed, you have to include your edges. The other thing you need is bounded, which means that you can't have your domain be arbitrarily big. It all is relatively close. So if you're closed and if you're bounded and your function is continuous, you must get a global max and you must get a global min. It has to occur. Now, this is not a trivial result. If you'd like to know why this is true, I have some wonderful classes you can take and derive it. It's a lot of fun. It's a lot of fun. It deals with topology, but for us, we're just going to take it as a fact. All right. So that's why, if you think about what was our goal for today, we said, look, we want absolute maximum min, continuous function, closed and bounded domain. So essentially we say, I want to be in the setting where I know I actually have an absolute max and an absolute min. So, how does the process work? With all of that out of the way, it actually becomes almost intuitive. We know it exists. So what we're going to do is we're going to look for the places where it could be. That's where we get to our making a list. In other words, we're going to channel the philosophy that we had from the very beginning of last lecture. We talked about critical points. Where can max and mins occur? They can occur where the gradient is 0, the gradient is undefined, or the boundary. So we're not going to worry about the gradient being undefined, but technically it's part of it. We don't run into those types of situations. So we say, okay, we'll start by saying, where is the gradient 0? Now you have to be a little bit careful. It's not just a matter of is the gradient 0, is the gradient 0, and is that point a point in my domain? So, as an example, maybe I'm looking in a region, and maybe my region is a triangle. That frequently happens that we like to use triangles. You'll see why very quickly why we like to use triangles. But this might be our domain. And we say, okay, well, here's a place where the gradient is 0, and here's a place where the gradient is 0. Do we include this point on our list, the one that I'm pointing to, which is inside our domain? Yes. Do we include this point on our list? No. Because it's not part of our domain. The list can only include pieces from our domain when we're making our list. So just be careful. There's a little note here that says, hey, you remember that stuff we talked about from last time? Where we talked about, hey, classify, take this fxx fyy minus fxy squared. Don't do that. It's not needed at all. We are just in the make a list phase. Okay, so that's the gradient. And essentially, one way to think about what number 1 is this is going to be our interior points on our list. What are points on the inside of our domain? Now we get to part 2. This is the long part. And it says, well, it might not just be on the inside, it might be on the boundary. So you have to check the boundary, all the boundary. Now, that doesn't mean we're going to test every single point, but what we do is we say, well, let's test the corners. We always include corners. They're just a given. And then for any other piece of our boundary, we say, well, hey, we can think of this boundary piece. It's not a two-dimensional region, it's a one-dimensional thing. So we can use parameterization to get it down to just a single variable. And once we get it down to one variable, then we can look for critical points using our single variable tools. So we're going to reduce dimension. So we've made a list. We have the interior points from step 1, the boundary points from step 2. We know for sure that all the maxes and mins are on that list. We also know that there's an absolute max and an absolute min. So it must be at one of those points. So the last 2 parts are, say, plug each one of those points into the function, and we see what the values are, and then we say, let's look at the outputs. The largest output, absolute max, and the smallest output, absolute min. And we're done. That's the process. So intuitively, it's not too bad. Just remember the song. You're making a list, and you're going to check it twice. The part that will take you the longest, where you will spend, I hate to commit myself, I would probably say 75 to 85% of your work is in step 2. This part will, if it hasn't made you go ugh yet, we'll get there pretty quickly.
Today, right?
No, we'll finish at least one problem today. At least one. Maybe 2. But let's shoot for at least 1. All right, any questions about the process? From here on out, it's practice. All right. Here we go. Find the global max and global min. By the way, global max and global min are the same thing as absolute max, absolute min. For the function, g of xy is x squared minus 4x plus 2y squared minus 4y plus 1 over the triangle with vertices at 0, 0, 3, 0, and 3, 3. Since they didn't provide a picture, we'll make one for ourselves. All right, so we put a grid in. Our domain is two-dimensional. We'll mark the points 0, 0. 3, 0 means we moved in the x direction 3 points. 3, 0. And then 3, 3 will be up here. And our region is this triangle. Okay, so that's our region. It is going to be closed and bounded, so that's cool. On a test, we would go to extreme lengths to make sure we emphasize closed and bounded. So, we're now going to go into our make a list. Before we start, are there any points that we are going to throw in for free?
1, 1, 2.
3, 3 is going to make our list, somebody mentioned. Anywhere else?
3, 0.
3, 0. Anywhere else? 0, 0. Now, your list can be huge, but ideally, you don't want to add lots of points that you don't need to. Adding more points won't give you the wrong answer, but it'll make you do more work, and it'll make the grader say, what was this student thinking? Not that they won't say that, but, let's not give them an excuse. So the corners are always freebies. I will say on past exams, when I've written problems dealing with absolute max, absolute min, throwing in the corners would give you like 2 points out of 10. And a lot of people got 0 on the problem because they wouldn't even like throw in the corners. Just like throw in the corners. Get a couple points. So, all right. Well, let's begin. So let's start by doing the interior. So for the interior, and remember that's the gradient equals 0. I shouldn't put f, I should put g, gradient g equals 0. Well, g sub x, 2x minus 4, and g sub y is 4y minus 4. Set these equal to 0. Do we see a point that satisfies the equations 2x minus 4 equals 0 and 4y minus 4 equals 0? Yeah, so this becomes x equals 2 and y equals 1, or 2, 1. Now, before we add it to the list, we should do a quick little scan. So if we mark off here, say we're being extra careful, we'd want to check, is 2, 1 in our domain? Yes. So it makes our list. All right, so we have our corners and our interior. All right. Now the fun begins. We have 3 boundary edges. So we're going to do this 3 times. By the time we get to the third one, we'll be in great shape. So we have the bottom, the right, and the other one.
Directional.
Well, many years ago, I said, and Mr. Slanty. And then I was told by my colleagues, that's offensive. And I was like, what? And, well, some people might be offended if they're Asian. So I went and asked my Chinese wife, is this offensive? And she was like, I don't understand. Why would it be offensive? Then I tried to explain to her, I guess it could be, I don't know. But so we'll just say bottom right other, so I don't have to get into trouble. All right, so those are the three, bottom right other. So which one do you want to do first?
Bottom.
Do the bottom. Okay, so the bottom curve. Think about how can you describe the bottom curve? Think of it as a curve. What is it? Yeah, this is like y equals 0. So what we can do is on the bottom, we can make our function look like g of x comma 0. So we're going to just put in y equals 0. And what do we get? Well, we get x squared minus 4x plus 1. And notice, it's a single variable function. We've reduced it down. Now that it's a single variable function, we can apply our tools. So we can give this a name. I'll call it b of x, for b for the bottom. So looking for critical points, take the derivative, 2x minus 4, set it equal to 0, and we get x equals 2. Now we have to interpret that. That's x equals 2 along the bottom, which would be there, that point there. Does that make our list? Yes. It's on our boundary. So 2 comma 0 makes our list. All right. Well, 2 more edges to go. The right and the other. Choose the right when the choice is placed before you. All right, so what describes the right curve?
X equals 3.
X equals 3. So I can think of this, I'll put it r as a function of y, is g of 3 comma y. So I'm using the description of the curve to rewrite the function to one variable. All right, well, so that says everywhere where we see an x, put a 3. So that's 3 squared minus 4 times 3 plus 2y squared minus 4 times y plus 1. Well, we can simplify. That's 9 minus 12 plus 1, which makes this 2y squared minus 4y minus 2. 9 minus 12 plus 1 is negative 2. A function of one variable. We're reducing dimension. So we use our Calc 1 tools. So we take the derivative. What's the derivative turn out to be? 4y minus 4. Set the derivative equal to 0. What point do we get? Y equals 1. And so that corresponds to 3 comma 1, which is here. Is that going to be on our list? Yes. All right. Well, that leaves us with the other one. So, for the other one, what describes this curve? Y equals x. So what can we do? So, O looks too much like Omicron and like 0. T, how about P of x? P of x. I'm going to write this as G of x comma x. So I'm just replacing the y by x. I could have replaced the x by the y, but the point is I want to get down to a single variable. All right, well, what does this become? X squared minus 4x plus 2x squared minus 4x plus 1, which is 3x squared minus 8x plus 1. Now what do we do? Same thing we did before. Take the derivative. 6x minus 8, set it equal to 0. We get out x equals 8 over 6, also known as 4/3. Now, x equals y, right? So Here, this is x equals y. We should have been making notes as well. The right is x equals 3. The bottom is y equals 0. So that gets us to the point 4/3, 4/3. So 4/3, 4/3 is roughly there. Is that going to be on our list? Yes, and I see you have a question.
So, like, you chose P of X for X, but could you done Y of Y and gotten the same thing?
Absolutely. Yep. You get to the same place. All right. Have we made our list? We can even check it twice to make sure we didn't miss anything. Don't forget corners. Easy to forget corners. Did you check every edge? Now, you may get an edge where you don't need to have any points in the middle. That does happen. It could just be the corners. So, and you may get a case where there's nothing in the interior. It happens. But you should check. All right, so we've made it through our make a list. What comes next? Well, we've checked it twice. Now we need to find out which points are nice. So how do you find out? Plug it in to the function. So now we have to plug each one of these points into the function. Well, I know one of them. Yeah, the 0, 0. That's pretty easy. What is 0, 0? 1. Okay, good. And now we just have to do the rest. All right. Okay. Which one should we do? Any preferences? 3, 3. Now we can do it on here. We can save ourselves a little work. You notice 3, 3, for example, is on this edge, the right edge. So I can come into the right and plug in y equals 3. 2 times 3 squared is 18. Minus 4 times 3 is minus 12. Minus 2, this becomes 4. All right. 3, 0. What will that be? Well, just the nice thing is you have lots of zeros. You get 9 minus 12, 0, 0, 1. Which is negative 2. 2, 1. All right. Oh, that's in the middle. We got to just plug it in. So that's 4 minus 8 plus 2 minus 4 plus 1. And, well, the 4's cancel. That's something. But 3 minus 8, negative 5. Okay. 2, 0. So that's 4 minus 8 plus 0 minus 0 plus 1. 5 minus 8, negative 3. 3, 1. Well, I'll take advantage here. We have the right-hand side. So I can plug in y equals 1 into here. Get 2 minus 4 minus 2. Which is negative 4. And 4/3, 4/3 is a number. No, we should work it out. Okay, so that's going to be 3 times 16 over 9. So I'm going to plug in 4/3 into here. Minus 8 times 4 over 3 plus 1. We can do a little bit of simplifying. That's 16/3 minus 32/3 plus, and 1 is 3/3. So that's 19/3 minus 32/3. 19 minus 32 is negative 13/3, which is negative 4.666 ... All right? So, We've now plugged it in. It's time for us to figure out which points are nice. How do we do it? We scan the list. And we say, where's the biggest number? 4. Where's the smallest number? -5. So, since we've run out of space there, we'll put it in here. Absolute max, global max, of 4 at the point 3, 3. Absolute min of -5 at the point 2, 1. So that's the process. All right, we have enough time to talk about one more problem. Any questions? All right. Now, the last problem for today. Find the global max and global min for h of xy equals 2x cubed plus 3y squared minus 12x for x squared plus y squared less than or equal to 4. If we just end up saying our list, I'll be very happy. Because once you have the list, the plugging in is just plugging it in. X squared plus y squared less than or equal to 4, what does that look like? Circle of radius 2. And we're less than or equal, so we include our boundary and everything on the inside. Okay, so always throw in your corners, right? So where are our corners? Ha 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 ha, very good. No corners. I think you meant to say, you know, that's how your calculus instructors would say it. All right, well, it's cornerless. Or maybe we're feeling cornered here, but we'll get there. Don't worry. All right. So we'll skip the corners for now. What else do we need to do? Well, we need to do our boundary and we need to do our interior. Let's get our interior out of the way. How do we do the interior? Gradient equals 0. So gradient of h equals 0. That becomes 0 has to equal h sub x, which is 6x squared minus 12. And 0 has to equal h sub y, which is 6y. 6y equals 0. That tells us y equals 0. 6x squared minus 12 equals 0. What does that tell us? Yeah, it tells us x squared equals 2. X equals plus or minus square root of 2. So we're getting square root of 2 comma 0 and negative square root of 2 comma 0. Are those in our domain? Yes, square root of 2 is smaller than 2. So we have 1.4 roughly is square root of 2. So we got those 2 points. All right, good. Well, we needed something on our list, so we made progress. Okay, so now we get to the boundary. All right. So, what's the goal? On the boundary, x squared plus y squared equals 4, because we're on the equals part. Our function looks like h of x comma y equals 2x cubed plus 3y squared minus 12x. I want to make my function look like one variable. One variable to rule them all. I don't want x's and y's, just a single variable. Can we use the fact that we're on our boundary to get down to one variable? And how do we do it? Sorry, what?
Make it the variable r.
Well, not make the variable r, but the word substitution is going to come into play here. Notice that there's only a single y, and it shows up as a y squared. That's a y squared. So that says, oh, on our boundary, y squared is 4 minus x squared. So on the boundary, this is the same as 2x cubed plus 3 times 4 minus x squared minus 12x. Which, if you work this out, that's 2x cubed minus 3x squared minus 12x plus 12 on the boundary. That's a function of a single variable. That's what we want. Yay, us! Okay, now what do we do with this? Well, but there's something we're also going to do. What are we going to do with this? We've gone down to one variable, and then what? We're looking for critical points, so we take a derivative. So, derivativize this thing. And what do you get? 6x squared minus 4x minus 12 equals 0. And at this point, now we can say, well, can we solve? Did I take the right derivative? Okay. Yeah.
3x squared.
Oh. 3x squared. 6x. That's even better for us. Thank you. Factor the 6 out. X squared minus x minus 2 equals 0. Thanks for catching my error. Does that factor? He asks us. He writes it like it factors. X minus 2, x plus 1. So that leads us to the points where x equals 2. Well, when x equals 2, it's right there. So that's 2 comma 0. At negative 1, we're here. So that gets us some other points, right? Because y squared is 4 minus x squared. So x equals 2 or x equals negative 1. At x equals negative 1, there's a punchline here. So wait till you hear the punchline, because this is a good punchline. Y squared is 3. So what is the y going to be? Plus or minus root 3. All right. Have we found all the critical points? And which one did we miss? 0, 0 is not a critical point. X equals 2 is on there. 2, 0. We got the interior point. Plus or minus square root of 2 comma 0. Yes, you got it. X equals negative 2. This is also a critical point. Now you might say, why? It's our corner. Now you might say, no, it's not. But wait. Where is this true? We got down to a single variable, but which x's is this true? From negative 2 to positive 2. So negative 2 is an endpoint for this function. So you have to include it as a point on your list. All right, so there's our list. Now you plug it in, and then you'll know. All right, we'll pick up again next time. Have a good day.